So we're going to take a look at a work problem here, and we'll talk about setting up the integral. We probably won't calculate it. So we have a cylindrical tank that's laying on its side 10 feet under the ground. The radius is 4 feet and the length is 10 feet. How much work is done to empty the tank up to ground level if it's full of water? So the situation is the tank is actually going to be laying on its side this way, and then the water is being emptied up to the surface over a distance of 10 feet. So let's talk about doing this via slicing. So what I'm going to do is I'm going to make a slice in here, so kind of give it 3 dimensions so you can kind of see, because I want to do a slice where the force is essentially constant. So I need to just do a slice that is perpendicular to the direction I'm moving, because that's where the force would be constant, because we have a varying force, because as the water is emptied we have less water, so the weight of the water is changing. So first off, let's talk about finding the, so we have our ith slice here. Let's talk about finding the volume on that ith slice. Now part of it's easy. I'm going to give it a thickness of delta x. I'll use x as my variable. So one of its dimensions has got a height of delta x. So what we have is a rectangular shape, kind of like a box. Now this length, no matter where my slice is always going to be the same. It's got a length of 10 feet, so that'll always be 10. And then I've also got some kind of distance going this way back here. Now depending on where my slice is, if it's up here it's more narrow, if it's down here it's more narrow, so that is something that's varying. So let's give that a name. For instance, we might call it W sub I. So there's our varying part. So we have 10 W sub I delta x. Now at this point what you should notice is we have a variable W sub I, but we're going to be integrating with respect to x. So we have to find a relationship between those two. So let's take an end view of our tank, and then I'm just going to draw a line for our slice. And I know that W sub I, I've called it going all the way across. And we probably should get also in what x sub I is. I'm going to let x sub I be the distance from my slice to the ground. There's an infinite different amount of ways we could do this, but I want to let the x sub I be the distance I'm going to move that slice, because I think it'll make my integral a little bit easier. W sub I is this guy. So we need a relationship here. Well, we need to think about what it is we know. So I'm going to put in the center of my circle, because I do know the radius of it, and then I've got some distances in here. So this side is 1/2 W sub I. This side, let's see if I can get an arrow in here. This side here, well, I know this distance is x sub I. I know this distance is 14 because I got 10 feet from the ground plus a radius of another 4 feet. So that side is 14 minus x sub I. So I have a right triangle where I know 3 of the sides, so kind of making a bigger picture so you can see it. That's my triangle here. I know this side is 4. I know this side is 1/2 W sub I. And I know this side is 14 minus x sub I. So I've got the Pythagorean Theorem here. So I have 14 minus x sub I squared plus 1/2 W sub I squared equals 4 squared. And now what I wanted to do was sub out W and sub in x sub I. So I'm going to move this to the other side, and I do want to square both of these. So I have 1/4 W sub I squared equals 16 minus 14 minus x sub I, the quantity squared. I'm not going to worry about multiplying this out right now. I'll take care of it in my integral. Last thing I got to do is I got to multiply through by 4 and then take the square root, or actually we could go ahead and take the square root now. Let's square root both sides. So I get 1/2 W sub I equals square root of 16 minus 14 minus x sub I the quantity squared. Or w sub I equals 2 times the square root of 16 minus 14 minus x sub I, the quantity squared. So there's the substitution I'm going to make for my w sub I. So now I have v sub I is equal to 10 times 2 times the square root of 16 minus 14 minus x sub I squared delta x. Now what I want to look for next is what is the force on the ith slice. So basically I have a basically when I multiply this by the density, I will have a force, because we're talking about water, but if we notice the units that we're in feet, and water has a density of 62.4 pounds per foot cubed. So what I'm going to do is I'm going to multiply this by my delta. I'm just going to call it delta for now. We could sub that in later. Times 20 times 16 minus 14 minus x sub I, the quantity squared delta x. So now I have the force on my ith slice. The next step is to turn that force into work. Now I'm just talking about the ith slice. So I have delta times 20. We did not need to multiply in gravity by this one because the units that we're in, this delta will already turn it into a force, times the square root of 16 minus 14 minus x sub I squared, and then we got to multiply by the distance it's getting moved. I'll put my delta x in, we can rearrange it later. Because of the way I label my diagram, x sub I is the distance that it's being moved, so times x sub I. So I've got work for the ith slice. I can now set up my integral. So I've got delta and 20, those can be pulled out of the integral because they're constants. X, I dropped the sub i's because now we're continuous, we're no longer in a discrete situation. That's 14 minus x quantity squared dx. The only other thing we have to consider is what our variables are going to be. So we need to think about how x varies. So we're integrating over x, and notice that it's going to, each slice is going to have to either go 10 feet to 18 feet. So that's our x here. So my limits are going to have to be 10 to 18. And so there's the integral that will calculate this, and when we're all done, the units are going to be foot-pounds. I'm going to leave it up to you guys to calculate the definite integral. It's actually not a bad integral. What you could actually use a substitution to take care of the x's and make it a little bit easier to deal with. So that's how we could set that one up.